Hi everyone, I'm Tirtha. I'm presenting this spotlight poster talk on behalf of my co-authors from the robotics group at ICRA, Australia. In this talk, I'll present some of our early results on fully autonomous climbing on unknown structures. As you can see in this picture, we have our robot Magneto, which is autonomously climbing a discontinuous test rig with plates of unknown layout and unknown magnetic adhesion. But first, to motivate the need for multi-limbed climbing robots in the real world, let's just have a look at this picture of a manual bridge inspection. Due to the complexity of the structure induced by the trusses, baffles, arches, and limited access portholes, it's quite hard to find a single robot that can completely map the structure and take a close-range inspection measurement to detect faults. While an aerial drone can inspect the exterior frame well, a multi-limbed climbing robot can maintain close contact and navigate surfaces of these structures, making it an ideal platform for close inspections, but also some maintenance and repair tasks as well. However, to do so, the robot would require highly dexterous mobility and ability to maintain reliable adhesion to the structure at all times. Motivated by these challenges, we had introduced Magneto, a magnetically attached enabled multi-limbed climbing robot previously. It has 3 degrees of freedom per limb with passive gimbals at its feet to allow adaptation to variations on the surface. Magneto is able to exploit its body flexibility to achieve complex maneuvers, performing dexterous mobility. But the challenge of adhesion remains generally unsolved. So how does the robot ensure that it remains in contact with often uncertain adhesion capability induced by the real-world effects? For example, uncertainty in real world stems from a variety of factors. Corrosion patches in the structure reduces magnetic adhesion. Maintenance, repairs, or augmentation of the structure introduces unmodeled protrusions like welds, plates, bolts, etc., which are often detrimental to a good latch. In addition, the complex structure, in most of the complex structure, not all materials may have the same alloy properties or the same paint thickness. This induces a completely different adhesion ranges at different foot contacts. Such challenges requires the robot to select safe contact points in real time to enable robust climbing behavior in the real-world environment. Basically, real-world adhesion is uncertain, and the robot has to deal with this. We address this by augmenting each of the robot's foot with a point cloud camera, providing detailed local perception, and an inductance sensor to detect metallic contacts. The robot effectively selects a set of suitable contact points by processing a local point cloud patch collected during locomotion. Even in the absence of a visual sensor, the robot can feel its way forward purely based on proprioceptive perception and contact-based validation. After sorting the contact points using a task-informed heuristic, the best candidate is validated by a pull test with a cascading decision tree to ensure that the contact point can be sufficiently supported and the robot can actually put its full load on that contact point. If the test fails, the next candidate is selected and the process repeated. Here in this video, we'll see the result of a pure contact feedback-based climbing. The white patch is a cardboard piece attached to the surface, which is non-ferrous. Without visual feedback, the robot doesn't know that its next step is unsuitable, and then the robot detects the bad contact and rejects it and finds another suitable foothold. The robot, in this case, you would see interacting with the surfaces with protrusions. The robot is also able to discard bad contacts because of the geometry. Again, to illustrate the point, we had turned off the visual sensing, which could identify these flaws, but we wanted to show the pure nature of proprioceptive sensing that enables us to validate the contact points and walk in so-called blind mode. Integrating both the visual and the proprioceptive sensing and a validation in the room shows the robot climbing both vertically and inverted or any other angle in a completely unknown a priori environment with layouts unknown and magnetic attachment unknown. The utility of the contact-based adhesion validation is something that we believe strongly in, which will have a huge impact in the deployment on real-world environments for such climbing inspection robots. Thank you for listening. Here's my contact details, and I'm very happy to receive feedback, criticism, or suggestions for any future improvements.